The Hartree-Fock self-consistent field approach provides us with an algorithm by which we can determine energy levels for various multi-electron atoms. It doesn't give us totally accurate energy levels. Remember, there's going to be a little bit of difference due to correlation energy and the fact that electrons are correlated with one another. However, it does a pretty good job, and it gives us a good qualitative picture of where the electrons are in a molecule. Now, I want to remind you that when we deal with these systems, typically the value of energy equals 0 corresponds to a separated, that is to say, separated electron and nucleus. So in other words, it would represent sort of an ionized atom, if you will. All right, so what that means is that when we use the Hartree-Fock method to determine an effective energy, that is based on the effective Hamiltonian with an averaged potential due to the other electron or electrons, that this is always going to be less than 0. So it represents, if you will, the energy to remove an electron. Well, it turns out that this is something that was noted by a fellow named Koopmans, and so it basically represents Koopmans' theorem that these energies are good approximations to the ionization potential. Now, we're not going to really go into much depth with Koopmans' theorem, but I do want to point out that ionization potential gives us another insight into these multi-electron atoms. If we were to chart as a function of atomic number, all right, so atomic number, that is to say the number of protons or the elements are listed along the horizontal axis, and along the vertical axis we were listing the ionization potential. So this is an energy. What would this look like? You've probably seen this chart before because it's often shown in general chemistry. But you start at hydrogen and you go way up, and the highest ionization potential is for helium. Then it comes way down, it comes up a bit, and then gradually increases again. And really what I'm drawing here is the result of Koopmans' theorem, not the actual measured ionization potentials, though it turns out the two are remarkably similar. So in fact, Koopmans' theorem does do a great job of reproducing what we would actually see in an experiment. Okay, the next level comes up like this, and then down, and so forth. And then there's a longer period up, and this is where the transition metals occur, and we go things like this. All right, so you see a gradual decline in the ionization potential, and that's because we're going to, electrons are farther and farther from the nucleus. We're going to outer shells of these atoms. Okay, but the structure on the inside here, this sort of jagged line that we see for the ionization potential is actually something that tells us really that we have electrons that are forming some kind of interior structure in the atoms. That is to say, they're filling some kind of orbitals. So this is, in a sense, an experimental evidence for the existence of orbitals. We also see experimental evidence for the existence of orbitals in photoelectron spectra. Okay, why am I making such a big deal out of this? Well, one of the primary approximations that is used in the generation of the Hartree-Fock method is the fact that we're going to take this multi-electron wave function, and there's no reason to suspect that it should behave this way, but we're going to treat it as though it were two functions of one electron each that just are multiplied by one another. So basically we're going to treat the overall wave function of the electron as though it is a product wave function of two one-electron wave functions. And we're going to actually do this for all of our multi-electron atoms. And it's in fact, this is the approximation that actually causes the Hartree-Fock method to not give us totally accurate answers, but to miss out on the correlation between electrons. Now, let me remind you some things that we learned about the Hartree-Fock method. The radial wave functions are the ones that seem to be most sensitive, if you will, to the electron-electron interaction. So sensitive So these are the ones where we're basically incurring perhaps the most error in our derivations. Okay, the angular wave functions are essentially the same as the ones we found for the hydrogen atom. Basically, it's the spherical harmonics, and these are not exact for these, but they are very similar to the ones for the hydrogen atom simply because these actually reflect not something that is energetically related, that is to say to these interactions, but they reflect the angular momentum of the electron. And it turns out that angular momentum is a pretty robust quality, at least in terms of its total, simply because it's a conserved quantity. The angular momentum squared of the electron, and we've seen that as the orbital angular momentum squared, but also can apply to the spin angular momentum squared, that these in fact are conserved quantities when they commute with the Hamiltonian. And they do for smaller atoms. As we get to larger and larger atoms, we find that there's a coupling between these two kinds of angular momenta, and they are not themselves coupled. They themselves are not conserved, but their sum, the total angular momentum, and I'm writing this very symbolically, don't take this as an exact mathematical expression, but the total angular momentum, which is the sum of the orbital and spin angular momenta, is a conserved quantity. So it gives us a handle on the angular part of the wave functions for these multi-electron atoms. Now remember that the Pauli exclusion principle basically tells us that each orbital can only hold 2 electrons. So if we do have these spatial functions that tell us where the electron is likely to be found in the atom, we can begin filling them up in a systematic fashion, but we can only put 2 electrons in each of them because they must be one spin up, one spin down, or another way to think of it is they must each have their own unique set of quantum numbers. All right, what this means now is that we can begin to build up larger and larger atoms by using this concept. I realize that this is something that you're very familiar with from general chemistry, but what you're probably less familiar with from general chemistry is that this concept is in itself an approximation. We don't really have a 1s orbital per se in an atom larger than hydrogen and helium. What we have is something that looks like a 1s orbital, and it has many of the properties of a 1s orbital, but it's a little bit different than the ones that we solve for when we solve those simpler atoms. All right, this certainly holds for things like 2p or 3d. These orbitals that we're used to seeing in higher and larger atoms, they have similarities, if you will, especially the angular parts have similarities to the hydrogen atom, but they're going to be different, and they're different because of the electron-electron repulsive interaction when you have a many-electron atom. All right, but if we assume that we have something that's close enough that we can still use these labels to describe these things, we can begin to construct, if you will, a description of the wave function for larger atoms using those orbital labels. So for example, for chlorine, we often describe this as a 1s2, 2s2, 2p6, 3s2, 3p5 configuration. Now what have I just done? Essentially what I've done is I've given you a census of the electrons in the chlorine atom. And I've basically assigned those electrons to various places where they live. So 2 electrons live in the 1s orbital, and 2 more live in the 2s orbital. 6 more live in the 2p orbital, 2 live in the 3s, and 5 live in the 3p orbital. So really all I've done is basically, as I said, giving you a census of where the electrons may be found. Now this census is useful in many ways because it helps us think structurally about how atoms are built up. However, it's faulty in the sense that while these electrons may occupy regions of space that look like these orbitals as they appear in the hydrogen atom, those orbitals in fact are distorted a little bit. Now what we can do, though, is we can begin to label these states based on these angular momentum, angular wave functions, because the angular momentum is something that we can begin to ascribe some reality to. So there is another aspect to this, though, and that's one that we want to explore in this particular lesson, and that's the following. If I look at this part of the electron configuration for chlorine, 2p6, what is that telling me? Well, it's telling me that the electrons that are in this part of the atom have orbital angular momentum of 1, which means that they have the projection of that angular momentum on the z-axis of -1, 0, and 1. We also know that those electrons, when they pair up in each of these possible orbitals, they have spin quantum numbers that can be plus or minus 1/2. That is, for each of those electrons. So that means that the energy shell that contains this particular type of orbital, which is n equals 2, has a variety of different ms and ml values. These are actually, I should have written this as ms because that's really what we're describing here. But we can write ml, ml, and ms as having the following contributing sets. We have ml equals -1, ms equals -1/2. We also have one for +1/2. All right, so that represents 2 electrons that are paired in the particular p orbital that has ml equal -1 in this atom. We also have orbitals that are described by these values of ml and ms. And finally, we have orbitals that are described by these values of ml and ms. Now, the question that I want to pose here is that in the hydrogen atom, all of these orbitals have the same energy. But once we add electron-electron repulsion and multiple electrons to this, these now have slightly different energies. And so one could fairly ask, if I have electrons that are populating chlorine in all these different places, these orbitals are going to be slightly different in energy, which is another reason why, for example, the electrons fill the 3s orbital first before they fill the 3p orbital as we're building up the periodic table. The 3p orbital have energies in a multi-electron atom that are slightly higher than those of the 3s orbitals. But even within the 3p orbitals, we're going to have a variety of states here. And the question that we want to ask, and the question we want to figure out how we might pose for these atoms, is which of these is going to be favored? Which one might have the lowest energy among all of these? Essentially what these are spin orbitals. So what we're going to be doing is examining the angular momentum of these electrons and using them to come up with a labeling system that will give us some clues as to how we can order their energies.